Welcome to the deep dive. Today, we're tackling something absolutely fundamental to the built environment, the very stuff of our sidewalks and skyscrapers, cement and concrete. Now, while it might seem like, just a mundane gray powder, trust me, the chemistry at play is surprisingly deep. And it has a history stretching back millennia.
That's right. And before we had our modern scientific understanding, well, ancient civilizations were already experimenting with materials that could harden underwater.
Really? Like who?
The Romans, for instance.
Yeah.
Our sources remind us they even coined the term hydraulic cement.
Ah, for binders that gain strength through reacting with water.
Exactly. It was a key insight, recognizing a chemical transformation, not just, drying.
And it's fascinating how this understanding sort of evolved organically. We have records indicating that way back, like the Minoan civilization in Crete,
Yeah.
they were using crushed ceramic potsherds added to lime, basically an early form of pozzolanic cement.
Wow. And the Phoenicians, too, right? Before the Common Era,
Yeah.
using hydraulic lime in Cyprus.
Yeah, it really highlights humanity's long-standing relationship with these materials. The core principle, it seems, is that certain materials, often with silica and alumina, can react with calcium hydroxide, if there's water present, to form these cementitious compounds.
Precisely. So for this deep dive, our mission is to systematically explore the hydration of the individual components of Portland, cement what we call the clinker phases.
Right. We're going to go through this chapter by chapter, really delving into the fundamental chemical reactions and the microstructures that result.
Our goal is to build a crystal clear understanding of exactly how cement develops its strength and those other essential properties.
Exactly.
And just so we're clear, this isn't a basic overview. We're aiming this exploration directly at those of you with a solid foundation in chemistry and material science.
Yeah, that means we'll be using the full proper chemical name, so tricalcium silicate, the calcium silicate.
No shorthand today. We want to really unpack the nuances of these reactions.
All right, so let's jump straight into chapter 3 of our source material. It's all about the hydration of these crucial clinker phases.
Right, starting with section 3.1, the intro.
Which really sets the stage for why this detailed understanding is so vital. The key takeaway here is that understanding these initial reactions is, well, foundational for predicting and controlling the final properties.
Absolutely. Whether we're talking about setting time, strength development, long-term durability, it all stems directly from how these individual minerals in the clinker react with water.
And like we touched on with the history, our modern understanding is built on centuries of, well, observation first, right?
Empirical observation, yeah, which eventually led to rigorous scientific investigation.
All right, let's get into the heart of the matter. Section 3.2, focusing on silicate hydration. This looks at the two main silicate minerals in Portland cement.
Tricalcium silicate and dicalcium silicate.
Let's start with subsection 3.2.1, tricalcium silicate hydration, also known as alite. When this hits water, what's the initial dance? What kicks things off?
Well, the very first steps of tricalcium silicate hydration are quite intricate. There's actually been considerable scientific debate.
Oh, about how it dissolves initially.
Exactly. There are two main competing ideas: congruent dissolution and incongruent dissolution.
Okay, what's incongruent?
The incongruent theory suggests that right upon contact with water, only calcium ions are preferentially released from the tricalcium silicate structure,
Leaving behind.
a surface layer that's rich in silicon oxide. The silica-rich layer then reacts with the calcium ions already in the solution to form calcium silicate hydrate.
Ah, okay. So a two-step process where the surface changes for a bit.
Sort of, yeah. The solid surface composition temporarily shifts.
And the other idea, congruent.
The congruent dissolution hypothesis suggests a more balanced initial breakdown. It proposes that tricalcium silicate dissolves more uniformly.
Releasing both calcium and silicate ions together.
Yes, releasing both into the water in roughly the same calcium to silicon ratio as they exist in the solid itself, which is 3:1.
Okay, so which one has more evidence?
Well, experimental evidence, notably from Barrett and colleagues, they observed the calcium to silicon ratio in the solution actually going above 3 very early on.
Above 3, what does that suggest?
It suggests that calcium silicate hydrate formation is rapidly consuming the silicate ions from the solution.
Right, pulling them out faster than the calcium.
Exactly, which leaves the remaining solution enriched in calcium. There are short-term experiments where they tried to minimize the time for that precipitation, indicated that when precipitation isn't a big factor, the ratio in the solution does indeed hover around 3.
So it seems the initial dissolution might lean towards congruent, but then the rapid formation of calcium silicate hydrate changes the solution chemistry almost immediately.
That seems to be the current thinking, yes. It sets the stage.
Now, after this initial contact and dissolution, we hit something called the induction period. What's significant about this stage? Why the slowdown?
The induction period. It's characterized by a relatively low rate of heat release, typically lasting for maybe a few hours. The precise reasons for this lull are still, well, debated in the scientific community.
But what's the main theory?
A prominent hypothesis involves the formation of a very thin, potentially poorly permeable layer right on the surface of the tricalcium silicate grains.
Like a barrier.
Sort of, yeah. It could act as a temporary barrier, hindering further rapid reaction between the water and the anhydrous mineral surface.
Is there evidence for that?
Well, Bertrandi's findings support it. They observed that the rate at which calcium ion concentration increases actually decreases if the tricalcium silicate has been slightly prehydrated.
Suggesting something is building up resistance.
Exactly. Think of it like a temporary skin forming on the reacting particle.
A temporary slowdown, like the system's catching its breath. So what kicks things back into high gear? What marks the acceleration period?
Right. That brings us to the acceleration period. And that's marked by a dramatic increase in the rate of heat release.
Okay, things speed up again.
Big time. This period is characterized by the rapid nucleation, the starting of new crystals, and growth of the hydration products.
Primarily calcium silicate hydrate and calcium hydroxide.
Yes, those are the main ones. And the formation of these solid phases from the dissolved ions releases significant energy, which we see as that increased heat evolution.
And this rapid formation is key for early strength, right?
Absolutely. It drives that initial strength development.
Can we influence this acceleration? Are there factors, levers we can pull?
Oh, definitely. The water-to-cement ratio is critical.
How so?
Well, a higher water-to-cement ratio generally gives more space for the hydration products to precipitate and grow. It also helps ions move around more easily through the water.
Facilitating diffusion. Makes sense. What else?
Interestingly, adding amorphous silicon dioxide, often as silica gel, can also significantly impact the rate.
Silica gel, how does that work?
Our source material shows heat evolution curves changing with different amounts of added silica gel. Basically, the very high surface area of this amorphous silica provides tons of sites for rapid reaction with the dissolved calcium ions.
More landing pads for the calcium ions to react faster.
Exactly, leading to faster formation of calcium silicate hydrate.
That makes sense. Now, there's also a mention of osmosis maybe playing a role in the shape of the calcium silicate hydrate gel.
Yes, that's an interesting concept. Osmotic pressure has been proposed as a factor influencing the development of those tubular or hollow fibrous crystals you sometimes see.
Within the gel forming around the grains.
Right. The idea is that differences in ion concentration across semi-permeable membranes formed by the very early hydration products could drive water movement, influencing local supersaturation and therefore how the crystals grow their morphology.
Fascinating. Okay, let's switch gears slightly. Subsection 3.2.2, decalcium silicate hydration, that's belite. How does this compare to tricalcium silicate?
Well, the hydration of dicalcium silicate, or belite, is generally significantly slower.
Slower reaction.
Much slower, yes. And it also releases less heat.
So its contribution to strength is different.
Right. Dicalcium silicate contributes more to the later age strength development, not so much the early setting and hardening.
And our source mentions dicalcium silicate can exist in different polymorphic forms. What does that mean practically?
Yes, it can crystallize into several different structures: polymorphs, beta, gamma, alpha, alpha prime H, alpha double prime H.
Wow, quite a few.
And these different forms are stable within specific temperature ranges, which you can see on the calcium oxide silicon dioxide phase diagram.
Do these different forms react differently with water?
They can, yes. They exhibit slightly varying reactivity. For instance, the beta form is typically the most common one in Portland cement clinker.
And that's the main one hydrating at room temperature.
Generally, yes. The gamma form, on the other hand, is structurally quite different and is usually considered non-hydraulic.
Meaning it doesn't really react with water to form binding phases.
Correct. So the specific crystalline structure present in the clinker directly impacts how the cement hydrates and gains strength over time.
So the manufacturing process is key there. Now, the main product from both silicates is calcium silicate hydrate, subsection 3.2.3. Our sources call it nearly amorphous to semicrystalline. What does that tell us?
Indeed. Calcium silicate hydrate, often called CSH, is the principal binding phase. It's responsible for most of the strength and durability.
But its structure is tricky.
Very. It lacks that long-range order of a perfect crystal, hence nearly amorphous to semicrystalline. This disordered nature made it historically challenging to pin down its exact atomic arrangement.
And the old term tabermerite gel reflects that.
Exactly, that early understanding of its somewhat gelatinous character.
But if it's a gel or amorphous, how can we have structural models?
Good question. While it doesn't have long-range crystallinity, it does exhibit short-range order. So scientists have developed models for its fundamental building blocks.
Like what?
One key concept involves silicate chains, specifically the Dreyer-Ketton structure.
Dreyer-Ketton.
Yeah, it means the repeating unit in the silicate chain has 3 silicon tetrahedra. These chains are thought to be linked together, mostly by calcium ions and water molecules, forming this complex, interwoven network.
Like linking 3 building blocks repeatedly in a chain, then connecting the chains?
Kind of, yeah.
And how does this relate to the calcium to silicon ratio in CSH? Our sources say it varies.
Right, the CS ratio isn't fixed. It can vary depending on formation conditions and the overall system composition.
Why?
Well, Taylor's hypothesis suggests these silicate chains can have different lengths described as polymers of 3N1 tetrahedra.
Okay.
Plus, the presence or absence of bridging tetrahedra within these chains and various structural defects can significantly influence the overall CS ratio.
So fewer bridging tetrahedra means?
Shorter chains and a higher CS ratio because you have fewer silicon atoms relative to the calcium ions holding things together.
Like Lego chains of different lengths with missing connectors changing the brick-to-connector ratio.
Got it. The sources also mention surface chemistry. Why is the surface of CSH important?
Yes, the surface is chemically very active. It plays a crucial role in the paste's behavior. Nodot's model focuses on the acid-base equilibrium of silanol groups.
Silicon bonded to hydroxyl groups.
Right. On the surface, at lower calcium concentrations, these silanol groups can lose a proton, becoming negatively charged.
And at higher calcium concentrations.
Then surface siloxo groups, silicon bonded to oxygen, also bonded to another silicon, or calcium can complex with calcium ions from the solution, also releasing protons.
So it's a dynamic surface interacting with the surrounding solution.
Very much so. It affects how CSH interacts with water, ions, and other phases.
And physically, what does CSH look like? Shape? Size?
It typically forms as extremely fine particles, often described as thin foils or sheets.
Generally in the nanometer size range. This contributes to the huge surface area of the gel structure. The sources mention these particles are often stacks of just 2, 3, maybe 4 of these thin layers.
Tiny sheets stacked up.
Yeah. And there's also a model describing an electrical double layer at the surface, suggesting complex electrostatic interactions with a pore solution.
And ultimately, why is understanding CSH in such detail so critical? The big picture.
Because the properties of cement paste and concrete, especially strength, but also permeability, durability, are overwhelmingly determined by the characteristics of this CSH phase.
It's the glue holding it all together.
Essentially, yes. The interconnected network formed by these tiny particles creates the rigid load-bearing structure. This interconnectedness at the nanoscale is what defines it as a gel in this context.
A system with strong cohesive forces making a continuous network.
Exactly. Our sources even reference solubility data showing the equilibrium conditions for metastable CSH phases forming early on, particularly during tricalcium silicate hydration.
Highlighting how those initial pathways dictate the final binder.
Precisely.
Okay, we've looked deep into the individual clinker phases. Now, Chapter 4 broadens out to the hydration of cement as a whole system. Section 4.1, cement hydration at room temperature. Let's start with 4.1.1, paste phase composition. When we mix everything together, what's the overall chemical environment like?
Right, when Portland cement hydrates, it's not just the solids reacting in isolation. You've got the liquid phase, too.
Just water initially?
Initially, yes. But very quickly, it becomes this complex solution saturated with various dissolved ions, calcium, sulfate, alkali metals, all coming from the dissolving cement particles.
A chemical soup?
A dynamic one, yes. Our sources have diagrams showing how the composition of this liquid phase changes over time as reactions proceed. Ion concentrations rise and fall.
Constantly evolving. And what about the solid products forming in this soup? How does the microstructure develop?
Well, around each cement grain, you get layers of hydration products forming, mostly CSH.
Shells around the grains.
Kind of. And as these layers growing from adjacent grains start to meet and interlock, they reach a critical point of cohesion.
The setting point.
It often correlates with that, yes. Our source suggests this cohesion point often aligns with a peak in the heat release curve, indicating significant structure development.
And these interconnected shells are key for strength.
Absolutely. Interestingly, after this initial outer shell forms rapidly, sometimes a small gap appears between the shell and the unhydrated grain inside.
A gap? Why?
It suggests the reaction is proceeding outwards, perhaps through that liquid-filled gap. The gap eventually gets filled in as more CSH forms later.
Like the original grain is consumed and replaced by its own hydrated shell that bridges to neighbors. Fascinating. Now, subsection 4.1.2, the crucial role of gypsum. Calcium sulfate dihydrate. We know it's vital. What's its fundamental purpose?
Calcium sulfate dihydrate, or gypsum, plays an absolutely essential role. It's a set retarder.
Meaning it slows things down.
Critically slows things down, yes. Without it, another key clinker phase, tricalcium aluminate, would react extremely rapidly with water.
Leading to?
Flash set, a very rapid, uncontrolled hardening within minutes, totally unusable for construction. Gypsum buys us time.
A chemical speed bump for tricalcium aluminate? How does it work? What's the mechanism?
The initial reactions mainly involve the tricalcium aluminate and the sulfate ions dissolved from the gypsum.
Okay.
This leads to the formation of ettringite. That's a calcium aluminum trisulfide hydrate.
Ettringite, what does it do?
It typically precipitates as very fine, needle-like crystals, often forming a coating on the surface of the tricalcium aluminate grains.
And that coating blocks further reaction.
That's one main hypothesis, yes.
Yeah.
A physical barrier preventing water from reaching the unhydrated surface.
Are there other ideas?
Another suggests that the sulfate ions themselves are preferentially absorbed onto active sites on the tricalcium aluminate surface, effectively blocking hydration that way.
So either a physical barrier or chemical blocking.
Or maybe a combination. Interestingly, our source mentions some conflicting findings about using sodium sulfate versus gypsum.
Oh.
Which suggests the mechanism might be more nuanced than just simple sulfate absorption. It's not entirely settled science.
Okay. What happens once the gypsum runs out?
Good question. After the gypsum is depleted, usually within the first 24 to 48 hours.
Depending on the cement and temperature.
Right. Any remaining unreacted tricalcium aluminate can then react with calcium hydroxide and the aluminate already in solution to form something else.
What's that?
Calcium monosulfoaluminate hydrate, often called the AFM phase. The sulfate concentration in the liquid is key here, controlling the equilibrium between different sulfate-containing solids.
And does the gypsum itself matter, like its fineness or how much we add?
Absolutely.
Yeah.
Gypsum fineness and the dosage are very important. Finer gypsum might dissolve more readily, giving a more immediate retarding effect.
And the amount?
The optimum amount should be enough to react fully with the tricalcium aluminate present, forming ettringite during that initial period, say the first day or two.
And temperature affects this?
Yes, temperature plays a significant role in determining the ideal gypsum content, affecting both dissolution and reaction rates.
What if you add too much gypsum? Are there downsides?
Yes, definitely. Excessive gypsum can cause problems later on, like expansion, potential deterioration of the concrete.
How?
It could be due to ettringite forming at later ages, after the paste is hardened. The growing ettringite crystals create expansive forces the hardened paste can't accommodate.
Sometimes called delayed ettringite formation.
Exactly, or internal sulfate attack, especially in cements high in tricalcium aluminate. Coarsely ground cement can make it worse, too, if large gypsum particles persist.
So it's a delicate balance, enough to retard, but not too much to cause later problems?
Precisely.
Okay. Subsection 4.1.3 looks at the effect of selected compounds, chemical admixtures. Let's start with calcium chloride, used as an accelerator, right? How does it speed things up?
Correct. Calcium chloride is a well-known accelerator, particularly for tricalcium silicate hydration. Several mechanisms are proposed.
Such as?
Maybe a catalytic effect on the surface reactions, stimulating CSH nucleation by increasing local calcium concentration, increasing the permeability of that early hydrate layer.
Making it easier for water to get through.
Potentially, yes. Also, changing the pore solution pH or increasing calcium hydroxide solubility.
And it affects how the CSH grows?
Yes. Interestingly, studies show that with calcium chloride, the CSH growth direction on tricalcium silicate particles is modified.
How so?
Instead of maybe forming a dense layer that slows things down, calcium chloride seems to favor growth perpendicular to the surface.
Leading to a more porous structure initially.
Possibly, yeah. Allowing hydration to continue for longer, perhaps.
But there are big drawbacks with calcium chloride in reinforced concrete, aren't there?
Oh, absolutely. Huge drawbacks. Despite accelerating strength gain, it significantly increases the risk of steel reinforcement corrosion.
Why? What's the mechanism there?
Primarily two things. It can potentially decrease the pH of the pore solution, making the environment less protective for steel.
And the other.
And it significantly increases the electrical conductivity of the pore solution because of the chloride ions. That facilitates the whole electrochemical corrosion process.
So even if some chloride gets bound up in the CSH.
A substantial amount often remains soluble in the pore water, free to migrate to the steel and cause corrosion. That's why standards strictly limit chloride content.
So acceleration, but at a potentially high cost to durability. What about other compounds? Sodium chloride, potassium hydroxide.
They can also act as accelerators to some extent, mainly by increasing nucleation sites for hydration products.
And retarders. Sucrose.
Yeah, the source mentions sucrose and other organics as retarders. The thinking there involves adsorption onto hydrating surfaces, hindering water interaction.
Or forming insoluble calcium compounds.
Right, forming calcium organic complexes that coat the surfaces.
Okay, moving to subsection 4.1.4, the effect of grinding aids. These are added during manufacturing.
Yes, during the final grinding stage of cement production.
What's their main job?
To make grinding more efficient. They increase the mobility of fine particles, stop them clumping together or sticking to the mill.
Resulting in finer cement for less energy.
Exactly.
What kind of chemicals are used?
Various types. Polyglycol phenol ether, heptane phosphonate acid, fatty acids, alcohols. Their effectiveness seems related to surface activity and molecular chain length.
Interesting, like unsaturated fatty acids being better than saturated ones.
That's one example mentioned, yes.
Any side effects from using these?
Well, they can sometimes make the cement powder dustier, especially if they produce very fine particles.
And that affects pollution control.
It can negatively impact electrostatic precipitators used to remove dust in cement plants. Some aids increase the electrical resistivity of the fine powder, making it harder to collect.
Got it. And the source shows data on how different aids affect the specific surface area.
Yes, it illustrates that connection.
Lastly, in this section, 4.1.5 briefly mentions chromium reducers. What's that about?
Those are sometimes added to deal with traces of soluble hexavalent chromium, chromium-6.
Which can form during production.
Yes, the reducers convert it to less harmful trivalent chromium, chromium-3.
Why?
To prevent allergic skin reactions, contact dermatitis, in people sensitive to chromium-6.
Okay, health and safety measure. That racks up room temperature hydration. Section 4.2 shifts focus. Hydration of cement in hydrothermal conditions. Elevated temperature and pressure.
Right.
Subsection 4.2.1 introduces phases in the calcium oxide silicon dioxide water system under these conditions. How different is hydration when you crank up the heat and pressure?
Well, reactions are significantly accelerated, as you'd expect. But importantly, these conditions can lead to different, often more crystalline calcium silicate hydrate phases compared to room temperature.
Different products form.
Yes, the thermodynamic stability shifts. Things that aren't stable at room temp might become stable, and vice versa.
What are some key hydrothermal CSH phases?
Important ones include different crystalline forms of tobermorite, like 1.1 nanometer or 1.4 nanometer tobermorite, also zonite and alpha-dicalcium silicate hydrate. And what forms depends on the conditions. Strongly dependent on temperature, pressure, and the starting calcium to silicon ratio. The source includes a table showing typical phases in hydrothermally treated cement pastes.
And subsection 4.2.2 goes into the conditions of formation and structures. What's the key insight there?
It discusses the specific T, P, and CS ratio ranges, where these individual hydrothermal phases tend to form and become stable. And it talks about their crystal structures.
Like compounds related to wollastonite.
Yes, and the decalcium silica group minerals, and other less common ones like calciochondrodite and phosphogite. These phases often have distinct crystal shapes and different physical properties compared to the room temperature CSH gel.
Different properties like?
Maybe higher thermal stability or different strength characteristics, for example.
So by controlling temperature and pressure, you can potentially steer hydration to make specific crystalline phases with tailored properties.
That's the powerful idea, yes. Hydrothermal treatment is used in some specialized applications to get specific material characteristics you can't achieve otherwise.
Very interesting. Well, that brings us to the end of Chapter 4, and seems like a great point to start wrapping up this deep dive into cement hydration chemistry.
Absolutely. We've covered quite a bit of ground, haven't we? Delving into those intricate reactions of the clinker phases.
Right, from the initial dissolution of tricalcium silicate and dicalcium silicate
To the formation and the complex nature of that calcium silicate hydrate binding phase.
We also looked at how the liquid phase composition matters. the absolutely crucial role of gypsum in controlling setting.
And the diverse effects of chemical admixtures and even grinding aids on the whole process.
And finally, we touched on hydrothermal hydration, forming those distinct crystalline phases under more extreme conditions.
And as we've seen, that interplay between tricalcium silicate, dicalcium silicate, tricalcium aluminate, and gypsum is really what dictates setting time, hardening rate, and long-term performance.
With the water-to-cement ratio, temperature, and admixtures being key levers we can use to control things.
Exactly, controlling the reactions and the resulting microstructure.
And yet, despite all we know, that calcium silicate hydrate phase, the real heart of concrete strength, is still actively being researched.
It is. Its nanoscale complexity keeps challenging researchers, which just shows how fundamentally important it is. Still lots to learn about its precise structure and how that links to macroscopic properties.
Which leads us to a final thought for you, our listeners. Considering this intricate chemistry we've explored, how might we further manipulate hydration at a molecular level?
To design future cements with even more precisely tailored properties, maybe more sustainable ones for our evolving construction needs.
Could that involve, say, even better characterization techniques for CSH?
Perhaps, or developing entirely novel cementitious materials that use these hydration principles in new ways. Lots to think about.
A truly compelling question indeed. Thank you for joining us on this deep dive. We really hope it's giving you a new, deeper appreciation for the, well, seemingly simple but remarkably complex world of cement and concrete chemistry.
Until next time.